All right, in this video, we're going to talk about feedback, which is really where the op amps become very useful and powerful. So the idea of feedback shows up in lots of different places in electronics, but also more broadly in science and engineering. And the idea is you take the output of the system and feed it back in as the input of a system, and that can lead to interesting and useful results. You'll see. So let's imagine we have the following circuit. So we have our op amp, and our non-inverting input we're going to connect to ground. Our inverting input, we're going to send some input voltage to this via a 1K resistor. And we're going to connect the output of this back to the input of this with a 10K resistor. Okay, so before we figure out what the op amp is going to do, I want to tell you the op amp cannot change its output instantaneously to reflect what's going on at the input. What really happens is, like, if the condition at the input is such that the op amp wants to output a high voltage, it will increase this output voltage until it gets to wherever it wants to be. So the output we can kind of think of as ramping up or ramping down to some value very, this happens very quickly, but that is, I think that is a useful way to think about it. So in other words, if this non-inverting input is higher than the inverting input, so if V plus is greater than V minus, V out is going to go up. If V plus is less than V minus, then the output is going to go down. So the output is only going to stay put when these two are the same. And really, they're not the same. It's that this difference is being multiplied by the gain, but the gain is so big. If we're outputting, if the happy value of the output is 5 volts, say, that represents only a 5 to 50 microvolt difference between these two. So if the output is at some stable value, the voltage difference between those is very nearly zero, and for our purposes, it is zero. And we'll put this into rules later on. Okay, so let's look at some actual numbers and see what happens with this. So let's say we have an input voltage of plus 1 volts. So for an input voltage of plus 1 volts, what happens at the output? So let's say when we turn this thing on, this starts at 0 volts and it says, well, should I go up or should I go down? Like the op amp is deciding what to do. So if V out is starting at 0 volts, that means that our resistor circuit here looks like this. We have plus 1 volt, we have 1 kilo ohm. I'm kind of turning this on its side. We have 10 kilo ohm, and we have at this end 0 volts. Now, at this point in between, this is connected to the inverting input. So this is important for 2 reasons. One, this is the voltage that we want to find to figure out what the op amp is going to do, right? And also, it is possible conceptually that there could be a current flowing in or out of the inverting input, but for our op amps, we know that ideally the input impedance is infinite, and even for real op amps, it's 1 million to 1 billion ohms. So we are going to assume there is no current in or out of this, like junction, we're not adding or subtracting any current, and that means we can use the voltage divider rule without worrying about anything that's happening over here affecting this. So in other words, the fact that there's no current lets us look at this and say 1 volt, 0 volt. To get this is 10 elevenths, right? 10 plus 1 is 11. So this voltage is 10 elevenths of our 1 volt difference, which is about 0.9 volts. Okay, so 0 volts gives us V minus of 0.9 and V plus is still equal to 0 because it's always equal to 0. So V minus is greater than V plus, which means V out wants to go down. Okay, so that's what happens if this starts at 0. What if this is at some different value, let's say minus 15 volts? So what happens if it starts at minus 15 volts? So in that case, we can draw the same voltage divider. I've kind of run myself out of room, but we'll try to cram it in. Plus 1, 1 kilo ohm, 10 kilo ohm, minus 15. So now, we still don't have any current going in or out of here, so we can still use the voltage divider. This is going to be 10/11ths of a 16 volt difference plus minus 15 volts because it's going to be that much above minus 15. Anyway, this is a good voltage divider exercise if you're not following this. This is going to be approximately equal to minus 0.5 volts. So if we have minus 15 at the output, that is feeding back into the input and changing our input so that V minus was equal to minus 1.5, V plus is still equal to 0, which means that V out now wants to go up. Okay, so something changes between 0 volts and 15 volts, and in fact, this suggests that there is a voltage in between these where it is stable, where there is some stable voltage where the system will be happy. And indeed, that is true. And I will write down what it is and then we will show why it is. So at minus 10 volts, V out is happy where it is. It doesn't want to go up or down. Okay, so let's erase this and let's analyze this minus 10 volts. So if this is minus 10 volts, our little resistor voltage divider, looks like this. So we have 11 volts across 11 kilo ohms, which means this is going to be right at 0 volts ideally. So, so if this is at 0 volts and this is at 0 volts, wouldn't you say, well, if our op amp is really ideal, shouldn't that give us 0 volts at the output? Well, yes, okay, but really this isn't going to be exactly 0. This is going to be like minus 1 microvolt or something like that, right? So this is some really tiny difference from 0, which then is, sorry, maybe that should be plus 1 microvolt, plus 1 microvolt. And so then when it's doing this differential amplification, it says 0 volts, 1 microvolt. Okay, so I multiply that by 1,000,000, and that's going to give me, 10 microvolts. 10 microvolts is getting multiplied by the gain of 1,000,000 and getting output as 10 volts, minus 10 volts at the output. So anyway, this minus 10 microvolts is close enough to 0 that this is, this plus 1 and minus 10 are still, like the minus 10 is still the right equilibrium value. Maybe it's a few microvolts off from that, but that's the idea. Okay. All right. So this is the idea of feedback, that this means that there is a single stable value of the output for the input. So this is negative feedback where increasing the output, if you step through this, increasing the output has the effect of increasing the inverting input, the minus input, and that has the effect of decreasing the output. So if the output tries to go high, it pushes itself back down to this equilibrium point. If it goes too low, well then this point becomes lower than this point and it pushes itself back up. So there is one stable value that this allows to happen. Okay, so why is this useful? So we can kind of analyze this now with what we know. So in order for this stability to happen, the difference between these is going to have to be some really small value, some number of microvolts, right? 10 to 100 microvolts or something like that. And that's way more precision than we're usually interested in for our voltages. So, so what that means is these are, these can be taken as being at very close to or essentially the same voltage in our analysis of these circuits. Okay, so anyway, the function of this circuit, I won't analyze further. I'll tell you what it does. So if Vin was equal to +1, we got V out of minus 10 volts. If you change the input to -1 volt, so if it's -1, we get an output of +10. So basically, that's just adding a -1 here is changing the minus signs of everything else, and this is what we end up with. If this input voltage is 0, then the output is also happy at 0 because we have our voltage divider, and that's going to make this point 0 in between. Anyway, so from these few points, you might be able to guess this circuit is an amplifier. It is amplifying the input voltage by a factor of -10. So this is an amplifier with a gain of -10. All right, so what happens if we have an input voltage of +2 volts? Well, the math would say +2 volts times -10 gives us -20. But of course, we can't have -20 volts if our op amp is limited to plus and minus 15. So a voltage of +2 in would only give us an output of minus 15 volts rather than minus 20 volts. So that's what the limits of this looks like. All right, so this circuit is called the inverting amplifier. And it turns out to be very useful, and also very simple to analyze once we get used to these op-amp circuits. What I wanted to point out, though, is that the gain of this amplifier, the amplifier gain, does not really depend on the op-amp gain. Like, our op-amp gain only went into the calculation to say that these two voltages were very close to each other, right? 10 microvolts apart or whatever. So the amplifier gain does not depend on the op-amp open loop gain. As long as it is big, right? It has to be big enough that this behavior that we're looking at happens. So as long as it is big, it doesn't matter if it's 10 to the 5th or 10 to the 6th or whatever. That is not going to change this gain number appreciably. So where is this gain number coming from? So that is coming entirely from the value of these resistors. So in this case, this is the 10K resistor over the 1K resistor. The ratio of these is giving us the gain. We'll learn how to analyze this later on. But this is all of a sudden really powerful because if you change the values of these resistors, you can change the gain of the circuit. So you could imagine an amplifier where you can turn switches and put different resistor values in and change the gain on the fly, or do sorts of things like that. Yeah, so we'll have a lot more analysis of the inverting amplifier to come, but I wanted to give you a taste of what this feedback looks like. And we're not going to have to analyze it like this every time. We're going to have some rules to put in place so we can say, if there is feedback, our system is going to follow these rules, and then the analysis of circuits like this becomes very, very easy. So that's something to look forward to next week.